Okay. Okay, thank you for pointing that out. So what we're going to do now is, so we're talking about Mercer's theorem. And what I would like to do is to do a little bit more in-depth like discussion here. So so let's do this. Suppose so H is a separable RKHS, which would be if K is a Mercer kernel, RKHS over X. And so the kernel is measurable, K. Usually we assume this without like a measurable kernel that's given, such that instead of that condition above, this is like more general than the Mercer's K. So if you just have the K of, so it's like a, this is a measurable, as I measure a space, measurable space, say. But like X and mu is a measure space. So mu is a measure on it. This is also sigma finite, if you really want. What you're going to assume is that K L P mu, which is which we define to be integral on the diagonal. So K X X so P over 2 d mu of X 1 over P. So I'll take basically, this is like the LP of root KXX. Okay, so if you look at this function, this is a univariate function on X, and this is the LP. So suppose that this is finite. Then all the functions in H will be in LP. Okay, so every function in the RKHS would be in the LP. So in other words, we can think of H as a subset of LP. Okay. As I mentioned before, LP in general is not a collection of functions, but basically you can think of this RKH as a collection of functions. This is like you can embed it in LP. So every function goes to a function like a equivalence class in LP. So there's this inclusion map. So there is a map that sometimes written, and in this book is written as identity. Like the map that maps every function to itself, but one side is you have the Hilbert norm, the other side you have the LP norm. Okay, so the identity map from H to LP, it's like you can also think of it as the embedding of H. This is also continuous. So the H is continuously embedded in the LP, and moreover, the adjoint is an operator like the transpose, adjoint of this, so the inclusion map. The adjoint of the ID is the following integral operator. So the integral operator that we had, so ID star basically, which goes from LP. So if you have a map that maps H to LP, the adjoint maps LP to H. I'm going to call this also S, not to be confused later with an S that we have. So if you call this SK, SK would be, if I take any function f of x, then it would be integral over xk, xy, f of y, d mu of y. So that's basically the integral operator that we looked at, but it what this is saying is that the integral operator, in fact, maps LP to H rather than to, so it gives you more information about the output. If you plug in, so if the kernel, if this kernel function is in the LP in this sense, the diagonal is in the LP, then this integral operator defined on LP basically is the output is in H. Okay, so the functions are more regular than the function in LP, because we also know that H is in LP, right? So definitely the output of this is in LP, but so what happens is if I call this SK, then I can call this then we can call this identity mapping that maps H to LP mu, this we can call it xk star. So that's the adjoint of sk. So I'm not going to prove, so if you're interested, you can try to prove this, that the adjoint of this inclusion. So there are a couple of things here. So the functions are all in LP. The inclusion map is continuous. That basically sort of is an upgrade of that. And then the adjoint is actually this integral operator. So if the adjoint is sk, then because if I take another adjoint, I get back the identity matrix. So I can think of, this is just a notation. I can think of sk as just, so this is, I'm going to call it sk star. Okay, doesn't matter. So you could have like call this ID and the other one ID star. But if I call this ID star sk, then this would be the adjoint. The adjoint, once you do it twice, you get back the same thing. So we have this situation. So there's this nice, oh, sorry, I made a mistake here. I did it, the adjoint would be from, so the adjoint would be continuous. The norm of this adjoint would be, sorry, the norm of this identity mapping would be bounded by that norm that we have over there, LP mu. So it's continuous means bounded. So the operator is bounded, but the bound is that. What I made a mistake here is yeah, the adjoint would not be, yeah, this is going to be tricky. So the adjoint would be from LP prime to H, and this holds for any basically F in LP prime. LP prime would be, yeah, because the dual, yeah, I should have that. So the LP space is not Hilbert space in general. Okay, so the dual, so adjoint goes from the dual of LP, which is LP prime, where, so you can identify the dual of LP with LP prime. We can just restrict ourselves to the case LP is equal to 2, so things are the dual. So to be like general, identity goes from H to LP. The adjoint of the identity goes from LP prime, which is identify the dual of LP, and to the dual of H, which is so basically H star, which is just equal to H. Okay, so this side is, so H is the Hilbert space, LP is not. So it's an operator from LP star. So the identity goes from this, and then the adjoint is LP prime mu to H. Okay, so that's the story. If you look at the case of most interest to us is P equal P prime equal to 2. So if P is equal to 2, then so these are the Euler exponents. Remember that. So if P is equal to 2, which means that this is just the P here is equal to 2, then this would be L2. LP prime would be also L2. So L2 is an inner product. So the adjoint operates from L2 again to Hilbert space. So we have this nice picture then. So LP is Hilbert space. And so LP prime mu would be equal to LP. So this is in general the dual. So the dual, it's actually not the dual of the dual of LP is all the function of on LP, but it can be identified with this. But let's forget about this for now. What I want to say is this interesting result. In this case, in the special case where we care about, what we have is like L2 mu. This by this SK is mapped to, so SK is mapping it to H. Okay, that's this integral operator here. This maps it to H, and then the identity map, which is the adjoint of this, maps it back to L2 mu. Okay, so this operator that goes from, if you look at this TK that we actually define, this operator that is basically the same operator that we have here. It's defined like because this SK is the inclusion map. It just doesn't, so you map F to SK of F, and then you just embed it exactly in L2. So this SK star doesn't change anything, just inclusion map. So SK, composition in SK star, that would give you so TK is basically SK applied to the function, and then you apply. So you take a function, you apply SK, and then you apply SK star. That's the integral operator, which is basically, it's the same sort of operator. So TKF. So maps sort of, so TK maps from L2 mu to L2 mu. So what this is saying is that the operator that we defined before, definitely sort of the functions are, so the thing is that the functions are definitely in, like once I apply the integral operator, the functions are in the Hilbert space, but also in L2. Once you view it as a function, like an integral operator from L2 to L2, you can view it as basically this product of these two operators. That's basically what it is. And the fact that this is the product, this means that this is a self-adjoint. So the main point here is that since TK can be written as SK star SK, it is a self-adjoint operator, which means like TK star. Once you take the adjoint, right, you know what happens. Like you get S and then TK SS. So this is just right. That the star is like a transpose. So it's equal to, the adjoint is equal to itself because it's a self-adjoint operator, and also so it's self-adjoint and also positive, right? So self-adjoint and also positive. It's like a matrix, right? You make like A transpose A. Okay, it's positive means positive semi-definite basically. So both self-adjoint and positive because it can be decomposed like this. And it also, moreover, is compact, which and also compact. It's a compact operator. Compactness we talk about that. Probably follows from that as well. Yeah, compactness. What is a compact operator? Like the image is basically pre-compact. So just accept this for now. It just follows from what we discussed. Except for now. This implies that there is a full eigen decomposition. So for example, symmetric matrices have a full set of eigenvectors, right? So there's like an eigen decomposition that you can do. There are eigenfunctions and eigenvectors. Sorry, it's eigenvalues and eigenvectors such that you can write. So for a symmetric matrix, A, there exists an orthonormal basis. Orthonormal basis of Rn consisting of eigenvalues, values of eigenvectors of A. So U1 up to Un, and the associated eigenvalues lambda1 up to lambda n. The thing is that even if they're repeated, there is a full orthonormal basis, and then you can write A as summation lambda I from 1 to n, ui transpose. This is called the spectral theorem for matrices. So symmetry basically is self-adjointness, and if you also know that if A is positive semi-definite, then this means that lambda i's are all non-negative. Okay, so exactly the same holds for compact. So compact self-adjoint joint operator on a Hilbert space. On a Hilbert space. L2 have a decomposition. Decomposition like this. So TK would be summation lambda I. I can write it as phi I. I'm going to write it like this. I from 1 to infinity, let's say. And what this means is that TK applied to a function is basically summation I from 1 to alpha lambda I, phi I, and then phi I inner product, basically. Phi I F, phi I, that's the meaning of it, right? So this, if you multiply by an X, you get UI transpose X. So you can just write it like this, forget about it. That's just a notation for this. So phi I, phi 1 up to phi n, like phi to infinity, these are like orthonormal. Orthonormal system of eigenfunctions, functions of TK corresponding. I guess I'm using mu here to be consistent. Corresponding to eigen values mu I, like mu1. Mu1 bigger than mu2, bigger than mu3, and they go to 0 because things are compact. Mu I converges to 0 as I goes to infinity. That's the compactness. So this series converges in L2. So what this means is that TK phi I is equal to lambda, like mu I phi I. In other words, integral k x y phi I y d mu y is equal to mu I phi I x. Okay, so the whole point was that tk can be decomposed like this. It's a self-adjoint operator. It's basically the composition of this integral operator and the inclusion map. And so it's positive, it's self-adjoint. Compactness you can show by the arguments that we actually like, by the results that we have. Then actually that requires a little bit of work, but it's doable. Then what you get is that there is this general theorem. This is called the spectral theorem. Spectral theorem for compact self-adjoint operators on a Hilbert space, which is basically essentially the infinite dimensional version of what you have for symmetric matrices. Then there's this decomposition. You can decompose the kernel matrix like that. I can always so this holds for any f in L2. Okay. Sometimes this is called ONS, orthonormal system. There's the orthonormal basis and there's the orthonormal system. Orthonormal system means you may not just fully like the span might not be the entire L2. Okay? I can expand it to do it, but then the mu's would be 0. Okay? So the rest of the mu's would be 0. So is this clear? Sort of clear. Right. So if you understand this, it's a very interesting idea. The main point is that the kernel integral operator has more properties. If things are in L2, and the kernel is in L2 in that sense, then the output is actually in the Hilbert space. Then you can just also map it into L2, but then you're basically like this is the inclusion map, and just shows that it's self-adjoint, so you can decompose it. The main point is that now these phi i's, they're in L2, but they can also take them to be in the Hilbert space. That's the critical issue. So in general, once you solve this, these integral equations, the phi's are in general, so they're guaranteed to be orthonormal in L2. So they're like this, and we also know that phi j in L2. This is 1 if I is equal to j, 0 otherwise. So they're orthonormal in L2, but in L2 things are like equivalence classes. They're not in this convergence in L2. It happens that I can actually assume these phi's to be belonging to the Hilbert space. The way that you can see this is we can actually view phi I not only as functions in L2 mu, but as elements of H itself. So they're actually functions. You can evaluate them. In order to see this, so you can think of this again as, let me see. So these are non-zero, basically, like the way I wrote it, non-zero. If you add zeros, you could like expand the whole L2. So what you can do is now, let's say, remember the SK is the same integral operator that maps, it maps the L2 to the Hilbert space. Okay, so SK same integral operator that is viewed as a map as a map from L2 to H. So what I can do is that I have these functions phi i's that are in L2. I can pass it through this integral operator. I'm guaranteed to have, so sk phi I, this would be in the Hilbert space. And then I'm gonna like divide it by mu I as well. I know that mu i's are non-zero, the way I define them. So this makes sense. So I call this phi tilde I. Okay, now this belongs to the Hilbert space by the way that we define this. You can think of it that way. And then we can also see that the okay, and then once I pass this phi tilde over to the L2, this is going to be basically the identity map. So what I'm saying is that this so we had this diagram, right? So you have tk L2 mu. This is sk star. So once I pass it through, this is basically the inclusion map. So what I get is basically now view it as L2. This part is like up to yeah, equivalence class. What I get is like SSK star phi I is like one more mu SK star SK. Sorry. Yeah, okay, so I get something like yeah, I get one mu tk phi I, right? This is phi I because that's right. So what I'm saying is that once I put this back into the L2, I get phi I. So what this is saying is I can treat this, so I can treat these as the representation of this, because this is like the inclusion. So every phi I has a representation in the Hilbert space, which is phi tilde, and phi tilde is basically like a function version. So every sort of every one of these eigen functions I can associate with this phi tilde, which is just basically once I pass phi tilde through sk, it's a function, and then once I put it back into the L2, it's still an eigenfunction. So this you can think of it as it's a tricky thing, but this is like a H representation of phi I. So we can think of these eigenfunctions phi I as just elements. So I'm not going to do phi tilde anymore. So I'm going to identify phi tilde I and like phi I. So I'm going to, from the start, say phi I is, I'm going to, for every equivalence class, I'm going to pick the one that's in the Hilbert space. That would be an eigenfunction and is also a function. So the key here is this relation now, phi I, because they're in the Hilbert space, I can just take the inner product here. So if I take the inner product in the Hilbert space as well, so they are orthonormal in L2. We know from the construction, we know that phi I, phi j in the Hilbert space, they're orthonormal. Sorry, in the L2 they're orthonormal. I equal to j, I not equal to j, but I can also compute the inner product in the Hilbert space now. Okay, this is a different inner product. So how do we calculate this? If I do mu I, mu j, I get mu I, phi I, mu j, phi j. This is in the Hilbert space. This is by definition sk now, phi I. You're sort of ignoring the. So we treat both as elements of H, and so this is the integral operator because they're eigenfunctions. So that's true. Then I get if you really want, this is like tilde, but that's fine. You get phi I sk star sk phi j, right? That's tk. That's the the adjoint property. And this is phi I. What is tk phi j? That's like mu j phi j. Sorry, this is now in L2. So once, so I have the Hilbert norm. Once I do the adjoint, things are in L2. I would get. So this is the tricky part. So inner products in L2. Once I move the adjoint to the other side, I'm taking these are you're viewing these as elements of L2. Remember, so this would be that, and so this would be mu j phi I phi j L2 mu. Now this is equal to mu j if I is equal to j, 0 otherwise. So what we have shown is that basically phi I phi j, I mean viewed as functions in H, they're actually orthogonal in the Hilbert norm as well. They're not orthonormal in L2, but it's just going to be 1 over, let's say, mu j, because I can cancel one of these, right? So you can cancel one of these. Mu j or mu I doesn't matter. So let's say mu I. I equal to j. Okay. So the interesting thing is that there is a sequence of eigenfunctions of the integral operator that can be viewed as functions of the Hilbert space as well. They are orthonormal in L2 and orthogonal in the Hilbert space. But the norm is in the Hilbert norm is 1 over mu h. So what this is saying is, let's say phi I L2 norm squared is 1, but phi I square is 1 over mu I. And because mu i's are going to mu i's are going to 0, so this goes to infinity as I goes to infinity. So what it is saying is that if you think of the Hilbert norm as measuring roughness, these functions are getting rougher and rougher. It's like they're higher frequency. So they're in L2, they're orthonormal, but when you look at the Hilbert norm, they're less smooth, and so they're sort of higher order components, basically. So is this sort of clear? So this is a little bit tricky, but if you understand, if you really want, there's like a tilde here. We're viewing them as functions in the Hilbert space, but we're identifying the tildes and then the phi. Okay. So this sort of, any questions? I suppose there's a lot of questions. It's not something which is very obvious if you haven't seen function analysis, but I just wanted to point out some of the niceties of this. Any questions? Let me just pause a little bit. You guys, yeah. It's not a projection, it's just an integral operator. It's like, if you want to look at it, it's just a matrix multiply. So think of the K as a matrix, right? This is like KF. If this is a matrix, this is a function. This is just the operator that it's like, you can think of it as like K summation Kij Fj, j from 1 to d. If K was finite dimensional, that's exactly what it would look like. So for a finite dimensional RKHS, okay, the kernel defined on d-dimensional space, this is just like a matrix multiplication. So this is the operator that maps basically F to KF. Think of K as a matrix. This is a general form for the general kernel. If the interesting thing is that if the kernel, so in the finite dimensional case, all of this is like sort of trivial because like this is definitely in L2, like all these things are finite. But in general, this may not be in L2. So the thing is that all this story holds even if K is not compact, and this K need not be continuous, just as long as this is finite, this operator, this result is like theorem 4.26 or something in the support vector machine book. This operator produces things in the RKHS. You start from a function here. The thing is that things gets continuous, more like when you take the integral, if I vary this a little bit on a set of measure 0, it doesn't change the integral, but the output, so you know that if you take the integral of a function, usually things become continuous, right? That's the idea. So if F is in L2, once I take the integral, things are now in the Hilbert space. So for example, if K is actually continuous, because this is in the Hilbert space, if K is continuous, all the functions in Hilbert, the H would be continuous as well. So this also would be a continuous function. Okay. Other questions? So this all holds without the Mercer idea. So the main thing is without the Mercer idea, this would be an orthonormal system. I can always expand it to, once you have like an orthonormal system, you can expand it to be just consider an orthonormal basis for the orthogonal complement of what they span, like the closure of phi i's, closure of the span of phi i's. There is an orthonormal complement. It has an orthonormal sort of, you can find an orthonormal basis for that complement and then patch, combine the two sets so you get a full orthonormal basis. The main interesting point here, this is like if you have a matrix for which like these are 0 at some point after a point, you can either truncate to that I from 1 to R, let's say rank R, and then the rest of the UIs are sort of arbitrary in the orthogonal complement. But you usually can expand this to basically after, so summation I from 1 to R, lambda I UI transpose plus summation like 0 UI transpose I from R plus 1 to, and these are not like unique in that sense, so they expand whatever remains. So you know this. This is the same story here. The main point here, which is very interesting, is this Mercer's if K is a Mercer kernel, this orthonormal basis happens to be an orthonormal. This orthonormal system happens to be an orthonormal basis. You don't have to extend it. The eigenfunctions just expand the entire L2. That's what I wanted to maybe mention. So under So if K basically, if K is a Mercer kernel, then that ONS consisting of phi I, these eigenfunctions, is actually O and B for H, ONS in it. Not for L2. This was in L2 and okay, so sorry. So what do you do? Let's do this. So the above shows that. So actually shows that it's not going to be an orthonormal basis for L2. It's going to be an orthonormal. So the above shows that root mu I phi I, this is an orthonormal system for H. Okay, because if I rescale them by root mu I, then they become orthonormal. If K is a Mercer kernel, it follows, in fact, that this is an orthonormal basis. That's what it is. So not only they're orthonormal, but they expand the entire H. So I can write, so this means this means that every F in H has a representation of the form summation alpha I root mu I by I for sequence alpha 1 or alpha 2. These are real numbers. Okay, Q1, this is an L2 of R. This is the sequence. And this is like, sorry, the infinity. Convergence in H, which is stronger than L2. And in fact, converges pointwise uniformly because of the Mercer's theorem. So this is a consequence. Maybe I'm going to come back and talk about it. So in this case, this is the fact that this is an orthonormal basis. This is follows from the so-called Mercer's theorem. Mercer's theorem. We have the Mercer's theorem here. Yeah, I don't have the Mercer's theorem here, but I'm going to come back next time and talk about this. But that's basically the idea. Yeah, I'll try to post the slide. Yes. The main point is once the dust settles, there exists an orthonormal basis of the Hilbert space in the case of the Mercer, consisting of just the eigenfunctions of that kernel integral operator. And these functions are also orthogonal in L2. The only difference is that the norm is different in L2 and in the Hilbert space. Okay, thank you guys. See you next time. Hopefully. Okay.